All right, so we're starting the logarithm chapter today. But before we get into the logarithm chapter, we're going to talk a little bit more about exponents, because logarithms, which is, I don't know, y'all know anything about logarithms?
Nope.
Okay, logarithms were a created math to deal with solving exponential equations that were tough to solve. Like, for instance, if I were to give you an equation like this, I doubt many of you are going to have trouble solving this equation, are you? It's not a big deal. Now, if I wanted to, and I'll show you this in a couple days, I could turn this into what we call a logarithm. And that mean the same thing. I'm guessing in your head you're thinking that this means 2 raised to what power will give me 8? Well, when you see a log base 2 of 8, what that means is 2 raised to what power gives me 8? And the answer to that question is 3. So this is equal to 3, just like x is 3 here. But the point is, somebody created a logarithm because I could type this in my calculator. In the old days, you didn't have a calculator, you had a table. Your book is so old. We keep reusing this textbook because it has great problems in it, but it's really antiquated. And in the back, they have log tables, because this book was created in the 80s. In the 80s, not everybody had a calculator. So if I wanted to do that, I had to go to my log tables and look up the base of 2, match it with the base of 8, and it would give me the value of 3. Not that you couldn't do this one in your head, but sometimes it's not a nice answer. Sometimes it's this. And I have no idea off the top of my head what power I'm going to raise 2 to get a 7. I know it's less than 3, right? Because 3 would give me an 8. So maybe it's a 2 point something, but it's some weird irrational number. Well, I could look that up, and those tables would give me accurate values to like 5 or 6 places, or maybe 2 or 3 places. And your calculator just spits them out instantly. Okay? But the bottom line is there's a link between a log and an exponential equation. Right? Not an equation that has exponents, like x cubed. That's a power equation, like a polynomial. An exponential equation, and you probably know a little bit about exponential equations. What things grow exponentially that you've heard of? Y'all know?
Interest.
Interest on a banking account, maybe, although it's pretty low interest. But the idea is that you put your money in there and the interest grows and your value grows over time, right? What else? Come on, y'all want something about this.
I mean, I guess today the stock market, but
Yeah, well, interest, stock market, yeah, hopefully, not always. I mean, sometimes it's more like this, but
yeah.
the idea is that you have exponential growth. How about population? Populations tend to grow exponentially, right? Because you have 2 people and they have kids, maybe they have 2 kids, and those 2 kids have more 2 kids or 4 kids, whatever. But usually populations are growing like this as well. Now, sometimes the population reaches a ceiling. Okay, like for instance, there's only so many resources on the earth. Can we keep going from a population of 7 or 8 billion to a population of 100 billion? I'm guessing there's not enough soil on the earth to produce enough food for that to happen. But so usually populations at some point start to flatten out based on the resources, and they become a different kind of curve called the logistic curve. But the bottom line is exponential curves are related to curves like this right here. Like if I had this curve, they're related to curves like this called logarithmic curves. And we're heading in this direction. But today we're going to talk about exponential functions and how they're related to the square root functions we just talked about, and how we can write square root functions as exponential functions. All right, and then we're going to talk about inverses and how these are related, and then we're going to move into logarithms. Logarithms, it's like learning a language. Okay, you guys already know how to multiply with bases and powers, like, right? Multiply like bases, add the exponents. You've got rules for that kind of stuff. You're going to have to learn new rules for these. The downside is you don't know them yet. You've never seen them before, so it's a new language. The upside is there's only so many rules, and once you get it and start to feel comfortable with it, these log problems become simple because there's only so many ways I can ask you stuff. All right? Historically, it's not like there's not a big heart when people in Algebra 2 think about logarithms. Usually second time through their junior year, they're like, oh, this makes so much better sense. And like any language, you're going to feel more comfortable with it as time goes on. But in a couple of weeks, which is all we're spending with this right now, it can be tricky. So my advice is really stay with me. Those of you at home, really stay with me on this. Ask good questions. Don't get behind. And I think we can be okay. All right? So I want to look first at, I think this is on page 29. And if you're with me on page 29 in your book, it looks like this. All right? So I want to walk you through some of these rules. These have nothing to do with logarithms. These have to do with our power rules. Now, you remember this rule? Something when it has a power to a power, you multiply the powers. Well, I want to kind of walk you back on this. Whenever I'm multiplying powers, it means I have x to the a to the b, or I guess you could have x to the b to the a. When I'm dividing powers, like when I have a fraction as a power, that's different. Now the a part is still like the power. This is like something to the a power. So you could still write this as to the a power like that. But a b in the denominator represents the power of the radical. Okay? So right here, if I have something like x to the 2/3, the 3 part represents the power of the radical. So that would be a cubed root. That's what that is. And then what's left over? X squared. And you could write that as x squared with the 2 there, like I have right like this, or you could write it as x squared there. Just depends on what's easiest for you when it comes to simplifying these expressions. So that's what that's saying. And if there's just a 1 there, then this is just another way to write a root. So a square root would be an x to the what? 1/2. A cube root of something would be an x to the 1/3. Because that 1 doesn't really do anything, does it? But if there's a number like an a or a 2 or anything like that, it does treat it like a power. So if I gave you something like a cube root of 2 to the 5th, you could rewrite that as 2 to the 5/3 power. If I gave you something like cube root of 2, since that 2 is really to the 1st power, you could write it as the 1/3 power of 2. Y'all seeing that? And some of you already know this because I've heard a couple of people comment on it. But anyway, I wanted to make sure that you are good on that as we start moving through here. Now your book tonight gives you lots of practice. It's some of it's good, some of it's kind of questionable. And I assigned a lot of problems. A lot of them says, put something in a certain form. I'm probably not going to ask you a lot of questions like that, but I'm trying to get you practice on changing from what we call radical form like this to exponential form like this. And the upside of that is this. You already have rules for multiplying exponents, bases with exponents. You already have those. You don't have rules for multiplying radicals unless they're in certain situations. Let me give you an example. If I were to say, what is the square root of x times the cube root of x? Do you know how to multiply those? I don't either as radicals. However, could I rewrite that as a x to a power? Okay, x to the 1/2, because that's a 2 and that's a 1. Could I rewrite that as a power? X to the 1/3. And now, what's my rule for multiplying like bases?
You add them.
Keep the base and add the exponents. So the advantage of doing this is sometimes I can rewrite it and then use a language I already know. Does that make any sense? Now, when I add 1/2 to 1/3, I get what? X to the 5/6. So if I wanted now to change it back into this radical form, I could use the 6th and call it a 6th root of x to the what? Of x to the 5th. And I could put the 5 on the inside or the outside. Now, with that in mind, you could make up a whole nother language for stuff like this. You could learn how to, you treat the 2 and the 3 like common denominators and adjust the powers. You can learn, there's all kinds of other stuff you can learn and you can adapt. But I'm trying to keep it at a minimum right now in Algebra 2 by making you not have to learn so much new stuff, and in a situation like this, recognize that you can use what you already know to get that stuff multiplied together. And also, sometimes it's helpful. Like you guys probably already know that the cube root of 16 is 2 cube roots of 2, right? Because that cube root of 16 has an 8 in it, and you know the cube root of that 8 ends up being a 2 on the outside. Go with me? Right? But look at this also. I could have written this cube root of 16 as the cube root of 2 to the 4th, which is 2 to the 4th. right? And 2 to the 4/3 is also 2 to the 1 1/3. So what I could have done is said, oh, 2 to the 1 1/3 is the same thing as, tell me if this makes sense to you, as 2 to the 1 plus 1/3, right? And again, this is something that you probably wouldn't want to do unless you kind of had the rule down quickly. But isn't that, take a good look at it, isn't that the same thing as this? 2 to the 1 times 2 to the 3rd. Now if you're like, I wouldn't have known that, but hold on. You would have known that like basis says keep the base and add the exponents, right? That's a rule, isn't it? Well, I can go backward with it. Well, the upside of doing this is saying, well, that means that at the very end of the day, I'm going to have 1, 2 on the outside and a cube root of 2 left over. So problems like this, the 5th root of 65, 61. If you knew that from your powers quiz was 3 to the 8th, right? And that's the same thing as 3 to the 8 fifths. If I wrote that as as a proper fraction, a mixed number, that's 1 3/5. That means I'm going to have 1 3 on the outside and a 3 to the 3/5 power left over, or a 5th root of 3 cubed left over. It's just another way of simplifying, and that question that you guys had on your test, it had a cube root times a cube root times a cube root, and had all those 2s or 3s, I forget which test you had, or I don't know which test you had, but it had a whole bunch of the same number. You could have done that this way. You could have figured out how many 2s you had. Say you ended up with 17 2s, right? You could have looked at that rather than think, how many 2 cubes do I have in there? You could have said, well, that's the same thing as that, right? Which is the same thing as 5 and what? 2/3? So that's 5 2s on the outside and a cube root of 2 squared left over. So these kind of things can be helpful to you, but again, it's just one more thing you could do. If right now you're like, I'm good, I got that on the test, I'm good, then you probably don't have to worry about this, but I'm just showing you other options for things that you might have. Right there. So, let me scroll down a little bit further. So something like this, the 4th root of 1024x to the 7th. If you look at this and you're like, oh, I would have been fine with that. Great. But if I think about that as 2 to the 10th x to the 7th, then the 4th root is 2 to the 10 fourths, x to the 7 fourths. And if I write them as mixed numbers, I get these 2 things, right? Right? Well, isn't that the same thing as 2 2s on the outside, 1x on the outside, and then I have what? The 4th root left over?
Yeah.
4th roots of what?
2 squared and x to the 3rd.
So 4th roots of 2 squared x cubed left over. So sometimes it's a nice, neat way to do it, but again, if you already know how and you're comfortable with it, you're going to be fine. Other ways of simplifying. I have 49 to the negative, that's supposed to be a negative 1/2. Now you might do this. You might think to yourself, okay, a negative means what? Negative exponent. Means put it in the denominator. So that would give me this, of 49 to the positive 1/2. And then a positive 1/2 is the same thing as a what? A square root. So that means a 1 over the square root of a 49, and that would give you a 1 over 7. And there's nothing wrong with that. But rather than converting it or simplifying it using exponents or whatever, I could have written 49 as what?
49, 7, 4 over 2. Or no.
Are you kind of track with me?
Oh, yeah.
Actually, I kind of did these backwards. I converted this to a radical. But with this in mind, changing the 49 to 7 squared, what's the rule on power to a power?
You multiply.
You multiply. What's 2 times a negative 1/2?
Negative 7 to the negative 2.
Hold on, the 2's would
7 to the
cancel.
negative 1, sorry.
So 7 to the negative 1?
So 1 over
1 7. 2 entirely different ways of going about this. Y'all seeing it? What about 8 to the 5/3?
8 to the 5th under a cube.
So with a radical form, I would say that that's the cube root of 8 to the 5th. Now you're going to have a lot of work there, actually. Or you could think, for each of these 8s, what's the cube root of 8 5 times? The cube root of 8 is, or remember, I can put the 5 outside.
2 is.
That's 2 to the 5th. Does that make sense? I can do the cube root of 8 and then raise it to the 5th power when I'm done. Or I could take the cube root of 8 to the 5th, which is 2 to the 15th, which I don't know off the top of my head. But either way, I can get there. But look, if I change 8 to 2 cubed and then raise it to the 5/3, what's power to a power tell me to do? Multiply. 2 to the 5th is left over. I'm showing you have two options now to do the exact same thing.
Wait, 8 to the 5th under a cube? Wouldn't you bring an 8 out and you'd have 64 inside? It'd be 8 squared left.
Which is what? What's the cube root of 64?
Oh,
4, and then the 4 times the 8. Which is
I
another way you could do it. So
see.
lots of ways you can do it, but this is just another option for you right here. All right, look at this. What about, and we've kind of already done this, square root of 8 times the 6th root of 8. Now, a few moments ago, I would say you don't have a rule for multiplying radicals that are different. And that's still true. We haven't developed that rule, although some of your brains are moving and you're like, I think I know what I would do. But right here, now we can talk about that rule if you want. I could use what I know, which is change square root of 8 to a what?
1/2.
8 to the half. 6th root of 8 to a
8 to the 1/6.
to the 1/6. And to multiply like bases with different powers, you do what?
Add 'em.
Keep the base,
So.
add the exponents, which gives me what?
8 to the 2/3.
8 to the 4/6, which is 2/3. Are you with me?
And then it's
And then I can just keep away from exponents all day now. What is 8 the same as?
8's the same as 2 to the 3rd to the
To the 2/3?
3rds.
And then what? Because 8 is a 2 cubed? The 3's would cancel because power to a power you multiply and you're left with a 4. Now you might notice something right here. 8 to the 1/2 right here is the same thing as what? 8 to the, it is, but isn't it also the same thing as 8 to the 3/6? 1/2, 3/6. I'll tell you what, I'm going to leave this 1/2 and change that to 3/6. So then wouldn't that mean that if that's a 2 and that's a 1, what I really did was multiply that and that both by a 3? Are you following me? I can do that because it's the same thing as multiplying this and this by a 3. That's how I got that. Well, that means I could take something like a root 8, which is a square root of 8 to the 1st, and multiply that by a 3 and that by a 3. And now I have a 6 root of 8 cubed, which is kind of what I ended up with. But that's a rule now that you have. And I don't make you use that rule right here. Some of you tried it. I don't remember what problem it was. I think it was something like, what was it? I think it maybe been like something like this. Is that what it was? Or this?
Yeah, it was something like that.
Something
No,
like
that's-
that?
I think it was that.
And I saw people do this. Cancel, cancel, 6. That you can't do. But I could have divided by 6, divided by 6. And what is a 1th root? A 1th root is no root at all. And you're left with 2 squared. But you were just trying to use rules we never talked about. And that's why a lot of people kind of got lost in that. Anyway, what about this thing? To divide. Do I know how to divide radicals that aren't the same radical?
No.
I don't. But I can change them to exponents. Numbers with exponents. So that's like an 8 to the what?
8 to the 1/2.
To the 3/6, which yes is a 1/2 if you've already gotten that far. And then divided by
4 to the 2/3.
4 to the 2/3, and couldn't I just do this?
Yep.
Now you can try to simplify these more. You could look at this and go, oh, well, I still don't have like bases. I tell you what, let me just leave that as a 3/6. So right here, I don't have a whole lot of like base stuff going on, but let me ask you, what if I change the 8 and the 4 both to a 2? Then I would be able to use that rule where like bases I can divide by subtracting their exponents. Check it out. Isn't 8 2 cubed?
To the 3/6.
And is it 4
2 squared. To
2 squared to the 2/3? So I get 2 to the what?
2 2.
What's
to
a
the-
3 times a 3 sixths?
2 to the negative 1 6.
Hold on. 3 times 3
Oh,
sixths.
2 to the 9 over 6.
Yes, or 3 halves. 9 over 6 is fine. And then on the bottom, what do I have?
2 to the 4 thirds.
2 to the 4 thirds. Can I divide like basis?
2 to the
Keep the base and what?
9 6 minus 8 6 1 6.
So 9 6 minus 8 6 ends up being 2 to the 1 6, which if you're going to go back to a radical,
2 under root 6.
the 6th root of 2 to the 1st. Now, there's nothing pretty about all this, but are you following me how I'm changing it to bases? Because I have rules for bases when it comes to multiplying. Yes, no? Okay. Now, let's come back to stuff like this. This is going to look a little bit or feel a little bit more familiar. Anybody got an idea of how to solve something like this? And keep in mind, a 1/3 power is the same thing as a what?
2
As a cube root of that to the first. Now, if I had it written as a cube root, what would you probably do to get rid of the cube root?
I make 3 27.
You cube both sides. Because isn't that what to a square root, I square both sides, right?
Yeah.
So keep in mind, I'm not going to have it written as a cube root, but a 1/3 power is the same thing, and doesn't the math still look the same? If I cubed both sides, you have a power to a power. What happens?
It makes
Multiply.
because
You multiply and then cancel, and that was my goal anyway when I was going to cube both sides. So I end up with an x squared minus 7 equals 27. Now from here, what would happen?
Add the 7.
So you're going to add the 7, and then that's a squared, so you're going to square root. Could I have 1/2 powered it?
Yeah.
That's the same thing as a square root, right?
Yep.
But the only thing I like about the square root is it's a little bit more familiar when you do this to remember it's going to be plus or minus. I don't know a lot of people right now that if they had done this and said, oh yeah, 1/2 power, I doubt many people would have gone plus or minus. But it's the same thing. If you do an even root or a 1 over an even number power, that's an even root. You got to remember it technically is absolute value, which gives you that plus or minus. Yes, no? Remember, if you have a question, ask it. Make sure we get you straight. So that's what I would probably stick to what I'm more comfortable with here. So what would I do on a 3/4 power?
Yeah.
Raise it to the 4/3 power, right? Because, and I'll show you another way, a 4/3 power on both sides, power to a power. If I multiplied, I'd get 12/12, which is 1. X to the first. Now, how do I simplify that? Okay, one option is to do the cube root of the 27 and then raise it to the 4th. Now, you could do, everybody with me?
3.
You could do 27 to the 4th and then cube root it, but do y'all want to do that?
Probably not.
I don't. And cube root of 27 is 3. 3 to the 4th is 81. I like that much better. Now, that's one option. Another option is to go, oh, I don't like the land that we're living in right now, so I'm going to change that back to the 4th root of x cubed. And then what would you do to get rid of the 4th root? Raise it to the 4th power. Well, you did that here with the 4th power. And it cancels, and you get x cubed. Now that's a big number, so I'm just going to leave it like that right now, because that's 3 to the 12th, 3 cubed to the 4th. I don't know my powers that high, but I'm hoping they get a little better. What would you do to get rid of the cube root? I mean the cubed.
Put a
Cube root it,
cube here.
and that would cancel that, and it's odd, so I don't have to worry about plus or minus. And then again, I could cube root the 27 now, and then raise it to the 4th, or I could raise it to the 4th and then cube root it. It's your call, but I kind of like the cube root first. And that would give me 3 to the 4th, which again we know is 81.
So you can.
But this is a little easier, isn't it? It seems like it's a little less math, but it's an additional way you can go about doing your problems.
And then like for the exponent, like you can still do 4 over 1 instead of 4 over 3, right? I feel like that would just in my mind would like simplify it better.
Here,
Yeah.
Yeah, like if I wanted to do it in 2 steps, I could do that first and cancel the 4's, and then I would have x cubed equals 27 to the 4th, and then I could cube root, and then I'd get to here. And at that point, I'd have to, again, go 3 to the 4th. But I like knocking it out in one swoop. I mean, you're normally getting rid of powers one time. Well, you could, again, the only reason why, guys, when you were solving this, the only reason why a square root was working is because a square root is the same thing as a 1/2 power. It's the same thing, except it's a little bit more difficult, I found, for most people to remember the plus or minus here. Because they're used to saying, oh, square root of x squared is the absolute value of x, therefore plus or minus. People don't think about it as much with the 1/2 powers. But again, because a 1/2 power is like an even root, you have to remember plus or minus when you're solving that equation. Anyway, what that's worth. All right, I'm going to show you a new principle. It is the most common sense principle on the planet, but it's a pretty big deal when it comes to solving. And you tell me if this makes sense. If I gave you a to the x equals a to the y, is it pretty clear that the x and the y would have to be equal for this to be true?
Yes.
If I gave you log of x equals log of y, is it pretty clear that x would equal y in this situation? Now, you don't know anything about logarithms, do you? Or not much. I mentioned, I guess, something. But this is still an option. I mean, this is a true statement. If I give you 3 to the 2x minus 4 equals 3 to the 12, so for this to be true, what has to be true? That would have to equal that. Does that make sense? Now, this is called the 1-to-1 principle. The 1-to-1 principle says, if everything on the left and the right looks identical, with the exception of 2 things, right? This thing and this thing, then I can set those 2 things equal to each other. And you can see that I did that on all of these. And then if I needed to, I could keep solving. Problem is, what happens when it doesn't look exactly the same? Can I still employ this practice? And the answer is yes, if I can make it look like that. Now, I might not be able to. With what you know, is there any way that I could make this 1-to-1 principle work? Now, I know you could solve this on your own, but if you're using the 1-to-1 principle, that is the same thing as what?
2 cubed.
And the 1-to-1 principle says, if these 2 things match, then these 2 things have to be equal to each other. But can you do that with something like this? No. That's where a logarithm would come in. We'll talk about that later. But if you can make them the same, then I can use the principle. So look at this first example. Can you think of a way to make these 2 things have the same base? Okay, so I'm going to start with the 32. That 32 is a 2 to the 5th, right? Now, do they look exactly the same?
Nope.
What can I change this on the left to?
To 5/3.
Now, do they look the same?
Yeah.
Now, the math says 1-to-1 principle. I can cancel those 2's. X must be 5/3. What about up there on the second example? Can I do that again? Now, they're not the same now, but could I rewrite these 2 numbers as the same base?
Yeah.
9 would be what?
3 being received.
Now, it's the whole 3 squared that's being raised to the x minus 3. And then 27?
3 to the cube. Wait, the last second cube is 3 to the cube.
I am, yes. So they still don't look the same, but what if I had power to a power? What does that tell me to do? Multiply that 2, the 2 of those together? Now, do I have the same base? 1 on each side, 1-to-1 principle? So 2x minus 6 would have to equal 3, 2x is 9, x is 9 halves. What about, I'm going to jump to the 4th one. What about this 4th one here? Now this looks totally different because it doesn't have 1 base, it has 2 bases. So what do you think I'm going to have to do at some point?
3, make it into the other base.
Find a way to get these 2 together. And I bet I can do it using my basic rules. So what number do you think would be a good base to shoot towards? A 3? So this one's already a base of 3. I'm going to leave it alone. What can I do with the 27?
3 to the 3x.
3 to the third to the x, and what can I do with the 81?
3 to the 4.
3 to the fourth to the 2x minus 1. Okay, now can I cancel my 3's out? That's not 1 to 1. That's not 1 to 1. That's 2 to 1. And we don't have that principle. So let's clean it up a little bit. I got 3 to the x plus 2 times 3 to the 3x equals 3 to the what?
8x minus 4.
8x minus 4. Everybody always, not everybody, a lot of people write 8x minus 1. Be careful, it gets distributed in when you multiply. Now, can I cancel the 3's now?
Yes.
No,
No.
because I don't have 1 to 1. I have 2 to 1. But do you have a rule on multiplying like bases? What is it? Keep the base, add the exponents.
X plus 2 plus 3.
So 4x plus 2. Now, can I cancel these?
Yes.
I have a rule now, 1 to 1 principle. So that tells me 4x plus 2 is 8x minus 4. 4x equals 6, x is 3/2. And that's simplifying and whatever. Y'all seeing this? Now I want you to look at the one we just did, and then I want you to look at this one that I already have the work done for. What's the major difference between this example I'm pointing to right here and this example right here? If you had to describe it. Both of them have bases with x's. What's the main difference? Everybody with me on this? Lock in. You what?
You substitute the 80.
That's true, but you're looking at the work. I'm talking about just when you look at the problem.
There's like pluses and minuses.
There's pluses and minuses. That needs to be your red flag. When you see that you're adding a bunch of these things together versus multiplying, I don't have rules for adding like bases with different exponents. I don't have those rules. Right? I don't have any rule that tells me that I can take this and somehow add these bases and get them together. I don't have that rule. So when you start seeing addition and subtraction in there, it becomes a factoring problem. Literally, you should be able to just smell it. Smell that it's a factoring problem. Not a powers quiz, but smell that it's a factoring problem right here. Here, I don't have that. And I have rules for taking like bases and adding them together. I have those rules, so I'm going to try to do that and use that 1 to 1 principle. Here, not so much. Okay, now, I know how to factor that. I do. And it wouldn't matter whether I had x squared and x, or y squared and y, or a squared and a. You're pretty comfortable with that, I think, for most of you. But here, I went and uglied it up with a 4 to the x, didn't I? Well, un-uglied it. Okay? If I get sick, what happens? I stay home, they send a sub in my place, and the place, they stay until things get better, and then they leave. If you see something nasty, make a substitution, just like they do here for me. So I'm going to take what's ugly and name it something pretty. And I'm going to replace that ugly with that pretty, and now it's pretty. And now I can factor it. Now I can solve what I factored, and once I get there, then like any good substitute, they leave and put the original person or value back in. And once I plug it back in, now I have a problem like we've been working on today. How do I solve a problem like that?
1 to 1.
1 to 1 problem, so I rewrite them, right, as a base of 2, 2 squared to the x, which is 2 to the 2x, 2 cubed, 1 to 1 principle, 2x equals 3. Solve that. Right here, 2 squared to the x is 2 to the 2x. If 2 to the 2x equals 2 to the first, 2x equals 1, x is a half. And you know why you don't have to check these answers like you do on square roots? Tell me about exponential equations. What do they look like? They look like those. Do they have any domain issues? They go forever left and right. You don't have to worry about it. What do square roots look like? They have lots of domain issues, tons of values that don't get plugged in there. But I don't have to worry about it with exponential functions, and this is an exponential function. So if I get answers, assuming I'm doing the math right, I'm good. And remember, the key to seeing the difference between these two, factoring problem, when you see that plus or minus in there, it's just a red flag for you. At some point, you'll become more familiar with it. But let me show you how I could really ugly these up. Like, this is what, another way to write it. You'll notice I didn't write it as 4 to the x squared. I wrote it as 4 to the 2x. But isn't it, hey, check it out, isn't that the same thing as either 4 squared to the x or 4 to the x squared? Isn't that the same thing? Because power to power I multiply. So when you see that, think 4 to the x squared. When I see that. Now I could have made it even worse. I could have changed that 10 to a 5 times 2, like in the original problem, which means like bases add exponents. Now when I look at that, I go, what in the world am I going to do with that thing? And I would think, what in the world? Well, what I'm going to do is go, well, it's certainly not ready now. Let me see if I can break that up, simplify it a little bit, maybe I can get somewhere. And then I could even change the 4 to a 2 squared to the 2x and have this. I could even move the 16 over and made it negative 2 to the 4th. And this is what Vestavia likes to do to us on a ciphering question, is spit that at us and see what we can do. And the more practice we do with these, the better you're going to get. For now, I'm going to take it easy on you, and well, kind of easy, I guess, and give you problems like we initially saw until you start getting more comfortable with them. All right? Okay, random practice until the bell rings. 9 to the 1/2, what would you do?
9 to the root.
Do what? So that's the same thing as the square root. Square root of 9 is 3. Great. Could you have also said 3 squared to the 1/2? And 2 times a half is 1, so 3. What about 9 to the negative 1/2? This is supposed to be a negative. Same thing but on the bottom, right? So the 1/2 means square root. The negative means put the square root on the bottom. So 1/3. But could I have also said 3 squared to the negative 1/2? Power to a power cancel. 3 to the negative 1, 1/3. So a lot of different ways to go about it. Jump down here to the bottom. Not the bottom, but where I'm pointing right now. 8 times 2 to the 1/2. How do I multiply like bases that aren't like? I don't.
2/3.
I can change it to 2 to the third. So 8 becomes 2 to the 3rd. Go with me? So what do I get now? Like bases? 2 to the 3 1/2 or 7/2. Now that would be exponential form. If I didn't want it in exponential form, but I wanted it in radical form, then could I have done this? That is the same thing as 3 1/2. What does that mean again? 3 2's on the outside, which is an 8 with a square root of 2 left over. But you could have looked at that and seen that, right? 8 to the square root of 2. Go down a little bit. What about stuff like these variables? How can I write these variable expressions in radical form? What's x to the 2/3? Cube root of x squared. Now, right here on this next one below that, is that the whole 2x to the negative 1/2? Or 2 times x to the negative 1/2? It's just the x, right? So the 2's fine. How do you do x to the negative 1/2?
1 over x to the 1/2.
Okay, you can start with that. So the 2 is still there on the top. And now at x to the 1/2. But this is radical form.
X root at root 2 to x, or root 2 over x. I don't even know. I get confused.
2
over
2 over
root x. Now, I would probably want to rationalize this in algebra 2, although I have a problem with people rationalizing variables, because how do I know it's irrational? What if x is 9? Then it's not irrational, is it? So you might see a book say, oh, that's 2 root x over x, but honestly, that's not so bad, because I don't know what x is yet. Okay, what about something like number 4? Not 4. This one right here, it says put it in exponential form. So I don't want the radical. What do I do with that 4? What does the x cubed become? Good. What does the y become? Negative 4 over 4, which is negative 1. And what's a better way to write this? Over a y? What about this right here? I could have just moved the y up right now if you don't like it there. Let's just do that, move the y up. Well, how do I do a cube root of all this stuff? X to the 2/3, y to the 1/3, because again, that's why the first, and then the cube root of the 8, 2. I mean, you can say 8 to the 1/3, but if it simplifies, I'd surely want to.
Oh, nice.
Struggling. It's about to ring on me. Okay, I'd love to be able to do a little bit more. We're just out of time. But hey guys, do this homework. Really be careful with it. Ask me questions if you have them, and let's start off strongly on this chapter, which you need them. Y'all are good one.
The other one.
Nope, she's in next year. Yep, super easy.
The multiple choice part?
Yep.
My
It's
boy.
literally what we did yesterday, just multiple choice.
Really?
Yep.
Yes!
How
How was the English quiz?
Dude, I finished like
Also, this is pretty good.
Yeah, I did.
It's like way better than I thought.
Yeah,
the first part was, oh, I thought it was terrible. I thought it sounded gonna be really boring. Now it's
7:30 is great.
brilliant.
Are you really looking at it and trying to find?
Let me stop this.
Oh, yes, please.